Carbon and its compounds. Introduction. In this chapter, we will be studying about some more interesting compounds and their properties. Also, we shall be learning about carbon, an element which is of immense significance to us in both its elemental form and in the combined form. Food, clothes, medicines, books, or many of the things that you listed are all based on this versatile element carbon. In addition, all living structures are carbon-based. The amount of carbon present in the Earth's crust and in the atmosphere is quite meager. The Earth's crust has only 0.02% of carbon in the form of minerals, and the atmosphere has 0.03% of carbon dioxide. In spite of the small amount of carbon available in nature, the importance of carbon seems to be immense. In this chapter, we will be looking at the properties of carbon which lead to this anomaly. Bonding in carbon, the covalent bond. We saw that ionic compounds have high melting and boiling points and conduct electricity in solution or in the molten state. We also saw how the nature of bonding in ionic compounds explains these properties. Melting and boiling points of some carbon compounds are given in the following table. Most carbon compounds are poor conductors of electricity. From the data on the boiling and melting points of the above compounds, we can conclude that the forces of attraction between these molecules are not very strong. Since these compounds are largely non-conductors of electricity, we can conclude that the bonding in these compounds does not give rise to any ions. Carbon overcomes this problem by sharing its valence electrons with other atoms of carbon or with atoms of other elements. Not just carbon but many other elements form molecules by sharing electrons in this manner. The shared electrons belong to the outer shells of both the atoms and lead to both atoms attaining the noble gas configuration. Before going on to compounds of carbon, let us look at some simple molecules formed by the sharing of valence electrons. So, two hydrogen atoms share their electrons to form a molecule of hydrogen H2. This allows each hydrogen atom to attain the electronic configuration of the nearest noble gas, helium, which has 2 electrons in its K shell. The shared pair of electrons is said to constitute a single bond between the two hydrogen atoms. A single bond is also represented by a line between the two atoms as shown in the figure. In the case of oxygen, we see the formation of a double bond between two oxygen atoms. This is because an atom of oxygen has 6 electrons in its L shell, and it requires 2 more electrons to complete its octet. So each atom of oxygen shares 2 electrons with another atom of oxygen to give us the structure shown in the figure. The 2 electrons contributed by each oxygen atom gives rise to 2 shared pairs of electrons. This is said to constitute a double bond between the 2 atoms. In order to attain an octet, each nitrogen atom in a molecule of nitrogen contributes 3 electrons, giving rise to 3 shared pairs of electrons. This is said to constitute a triple bond between the 2 atoms. Carbon is tetravalent because it has 4 valence electrons. In order to achieve noble gas configuration, carbon shares these electrons with 4 atoms of hydrogen as shown in the figure. Such bonds which are formed by the sharing of an electron pair between 2 atoms are known as covalent bonds. Covalently bonded molecules are seen to have strong bonds within the molecule, but intermolecular forces are small. This gives rise to the low melting and boiling points of these compounds. Since the electrons are shared between atoms and no charged particles are formed, such covalent compounds are generally poor conductors of electricity. Versatile nature of carbon. The numbers of carbon compounds whose formulae are known to chemists was recently estimated to be about 3 million. This outnumbers by a large margin the compounds formed by all the other elements put together. The nature of the covalent bond enables carbon to form a large number of compounds. Two factors noticed in the case of carbon are: carbon has the unique ability to form bonds with other atoms of carbon, giving rise to large molecules. This property is called catenation. These compounds may have long chains of carbon, branched chains of carbon, or even carbon atoms arranged in rings. In addition, carbon atoms may be linked by single, double, or triple bonds. Compounds of carbon which are linked by only single bonds between the carbon atoms are called saturated compounds. Compounds of carbon having double or triple bonds between their carbon atoms are called unsaturated compounds. Silicon forms compounds with hydrogen which have chains of up to 7 or 8 atoms, but these compounds are very reactive. The carbon-carbon bond is very strong and hence stable. This gives us the large number of compounds with many carbon atoms linked to each other. Since carbon has a valency of 4, it is capable of bonding with 4 other atoms of carbon or atoms of some other monovalent element. Compounds of carbon are formed with oxygen, hydrogen, nitrogen, sulfur, chlorine, and many other elements, giving rise to compounds with specific properties which depend on the elements other than carbon present in the molecule. Saturated and unsaturated carbon compounds. Another compound formed between carbon and hydrogen is ethane with the formula of C2H6. In order to arrive at the structure of simple carbon compounds, the first step is to link the carbon atoms together with a single bond and then use the hydrogen atoms to satisfy the remaining valencies of carbon. 3 valencies of each carbon atom remain unsatisfied, so each is bonded to 3 hydrogen atoms, chains, branches, and rings. We mentioned the carbon compounds methane, ethane, and propane containing respectively 1, 2, and 3 carbon atoms. Such chains of carbon atoms can contain tens of carbon atoms. The names and structures of 6 of these are given in the following table. But let us take another look at butane. If we make the carbon skeleton with 4 carbon atoms, we see that 2 different skeletons are possible. Filling the remaining valencies with hydrogen gives us. We see that both these structures have the same formula C4H10. Such compounds with identical molecular formula but different structures are called structural isomers. In addition to straight and branched carbon chains, some compounds have carbon atoms arranged in the form of a ring. For example, cyclohexane has the formula C6H12 and the following structure. Homologous series. You have seen that carbon atoms can be linked together to form chains of varying lengths. In addition, hydrogen atom or atoms on these carbon chains can be replaced by any of the functional groups. The presence of a functional group such as alcohol dictates the properties of the carbon compound regardless of the length of the carbon chain. For example, the chemical properties of CH3OH, C2H5OH, C3H7OH, and C4H9OH are all very similar. Hence, such a series of compounds in which the same functional group substitutes for hydrogen in a carbon chain is called a homologous series. Nomenclature of carbon compounds. The names of compounds in a homologous series are based on the name of the basic carbon chain modified by a prefix, phrase before, or suffix, phrase after, indicating the nature of the functional group. Naming a carbon compound can be done by the following method. Identify the number of carbon atoms in the compound. A compound having 3 carbon atoms would have the name propane. In case a functional group is present, it is indicated in the name of the compound with either a prefix or a suffix. If the name of the functional group is to be given as a suffix, the name of the carbon chain is modified by deleting the final E and adding the appropriate suffix. For example, a 3-carbon chain with a ketone group would be named in the following manner. Propane minus E is equal to propan plus 1, which is equal to propanone. If the carbon chain is unsaturated, then the final ane in the name of the carbon chain is substituted by ENE or YNE as given in the table. For example, a 3-carbon chain with a double bond would be called propene, and if it has a triple bond, it would be called propyne. Chemical properties of carbon compounds. Combustion. Carbon in all its allotropic forms burns in oxygen to give carbon dioxide along with the release of heat and light. Most carbon compounds also release a large amount of heat and light on burning. C plus O2 gives CO2 plus heat and light. Oxidation. Carbon compounds can be easily oxidized on combustion. In addition to this complete oxidation, we have reactions in which alcohols are converted to carboxylic acids. CH3NCH2OH with alkaline KMnO4 plus heat or acidified K2Cr2O7 plus heat gives CH3COOH. We see that some substances are capable of adding oxygen to others. These substances are known as oxidizing agents. Alkaline potassium permanganate or acidified potassium dichromate are oxidizing alcohols to acids, that is, adding oxygen to the starting material. Hence, they are known as oxidizing agents. Addition reaction. Unsaturated hydrocarbons add hydrogen in the presence of catalysts, such as palladium or nickel, to give saturated hydrocarbons. Catalysts are substances that cause a reaction to occur or proceed at a different rate without the reaction itself being affected. This reaction is commonly used in the hydrogenation of vegetable oils using a nickel catalyst. Vegetable oils generally have long unsaturated carbon chains, while animal fats have saturated carbon chains. You must have seen advertisements stating that some vegetable oils are healthy. Animal fats generally contain saturated fatty acids which are said to be harmful for health. Oils containing unsaturated fatty acids should be chosen for cooking. Substitution reaction. Saturated hydrogen carbons are fairly unreactive and are inert in the presence of most reagents. However, in the presence of sunlight, chlorine is added to hydrocarbons in a very fast reaction. Chlorine can replace the hydrogen atoms one by one. It is called a substitution reaction because one type of atom or a group of atoms takes the place of another. A number of products are usually formed with the higher homologues of alkanes. CH4 plus Cl2 gives CH3Cl plus HCl in the presence of sunlight. Some important carbon compounds: ethanol and ethanoic acid. Properties of ethanol. Ethanol is a liquid at room temperature. Ethanol is commonly called alcohol and is the active ingredient of all alcoholic drinks. In addition, because it is a good solvent, it is also used in medicines such as tincture iodine, cough syrups, and many tonics. Ethanol is also soluble in water in all proportions. Consumption of small quantities of dilute ethanol causes drunkenness. Even though this practice is condemned, it is a socially widespread practice. However, intake of even a small quantity of pure ethanol, called absolute alcohol, can be lethal. Also, long-term consumption of alcohol leads to many health problems. Reactions of ethanol. Reaction with sodium. 2Na plus 2CH3CH2OH gives 2CH3CH2O minus Na plus H2. Alcohols react with sodium, leading to the evolution of hydrogen. With ethanol, the other product is sodium ethoxide. Reaction to give unsaturated hydrocarbon. Heating ethanol at 443 K with excess concentrated sulfuric acid results in the dehydration of ethanol to give ethene. CH3 minus CH2OH with hot concentrated sulfuric acid gives CH2 equals to CH2 plus H2O. Properties of ethanoic acid. Ethanoic acid is commonly called acetic acid and belongs to a group of acids called carboxylic acids. 5 to 8% solution of acetic acid in water is called vinegar and is used widely as a preservative in pickles. The melting point of pure ethanoic acid is 290 K and hence it often freezes during winter in cold climates. This gave rise to its name glacial acetic acid. The group of organic compounds called carboxylic acids are obviously characterized by a special acidity. However, unlike mineral acids like HCl, which are completely ionized, carboxylic acids are weak acids. Soaps and detergents. Most dirt is oily in nature, and as you know, oil does not dissolve in water. The molecules of soap are sodium or potassium salts of long-chain carboxylic acids. The ionic end of soap dissolves in water while the carbon chain dissolves in oil. The soap molecules thus form structures called micelles, where one end of the molecules is towards the oil droplet while the ionic end faces outside. This forms an emulsion in water. The soap micelle thus helps in dissolving the dirt in water and we can wash our clothes clean. Take about 10 ml of water each in 2 test tubes. Add a drop of oil, that is cooking oil, to both the test tubes and label them as A and B. To test tube B, add a few drops of soap solution. Now shake both the test tubes vigorously for the same period of time. Can you see the oil and water layers separately in both the test tubes immediately after you stop shaking them? Leave the test tubes undisturbed for some time and observe. Does the oil layer separate out? In which test tube does this happen first? Have you ever observed while bathing that foam is formed with difficulty and an insoluble substance, that is scum, remains after washing with water? This is caused by the reaction of soap with the calcium and magnesium salts, which cause the hardness of water. Hence, you need to use a larger amount of soap. This activity demonstrates the effect of soap in cleaning. Most dirt is oily in nature and as you know, oil does not dissolve in water. The ionic end of soap dissolves in water while the carbon chain dissolves in oil. The soap molecules thus form structures called micelles, where one end of the molecules is towards the oil droplet while the ionic end faces outside. This forms an emulsion in water. The soap micelle thus helps in dissolving the dirt in water and we can wash our clothes clean. This problem is overcome by using another class of compounds called detergents as cleansing agents. Detergents are generally ammonium or sulfonate salts of long-chain carboxylic acids. The charged ends of these compounds do not form insoluble precipitates with the calcium and magnesium ions in hard water. Thus, they remain effective in hard water. Detergents are usually used to make shampoos and products for cleaning clothes.